Hello and welcome to another CS200 mini lecture. Today we begin Chapter 10, Memory Management, and this lecture will follow Chapters 10.1 through 10.3. Let's get started. If you recall from the end of Chapter 9, we introduced array lists. Array lists are unlike arrays because arrays, they're immutable, meaning they can't be changed once they've been allocated. We only can make a change by making a copy of the array with the changes to it. An array list, we can make modifications to the array, so it's a mutable object. One of the issues we have is because the space is allocated much like an array, we have an issue if we try to add rows to the middle. Let me explain with an example. Let's say we have the following array list. We've got 7 items here, and they're in order. So they're in sequential order, and we want to add another value. Say we want to add the value 23. The place where that will go is between 1 and 30. So the only way an array list can handle this is by shifting the elements down to make room for 23. Now this might seem like it's inconsequential with just 7 elements, now 8, but it actually has a performance hit, which the book tries to illustrate. We also have the problem when we delete an element, we have to shift them all back. So the example the textbook gives, let me show it to you, and let me run the code. So this is the code that is brought over from the textbook. And in this one, it gives us the ability to add and remove items from an array list. Okay, so remember, I need to import Java util array list, and because we'll be prompting the user, we'll also include Java util scanner. So we build this class array list add remove, and we've got our main, and then we declare a scanner object. Then we declare an array list. Remember, this is how we define our array list. And it will have integers in there. Then we define a couple of different variables. So we'll prompt the user for the size of the array list and then the number of adds. And you can see here that what we're going to do is we're just going to add a bunch of values. And so we're going to write, and then we're going to do additions at the end, and we're going to do additions at index 0. So it's going to push them all down. And what we're going to do is we're going to take a look at the time that this takes. So let's go ahead and run this. So I'm going to set it up to do 150,000. That's the number of elements, and we're going to add 50,000 to it. So you can see these are done pretty fast, but when we do additions at index 0, which means we're pushing them all down, you can see how much slower this works compared to what we saw before at the top. So these were done pretty fast. So if we're adding to the end, it's pretty fast. But if we do it starting with index 0, it's much slower. And then if we do removes, it's also slow. And that's the effect that we see, which makes it very inefficient when we want to use array lists to do this kind of work. So one way we can resolve this is by using a linked list. Now there's different types of linked lists. There's single linked and there's double linked, which allows you to go back and forth. But for now, we're just going to assume that we're going to go in one direction. Okay, so this single linked list works in a different way. Remember, an array list allocates memory, and all the different elements are in contiguous memory. But with a linked list, we can have different memory addresses and just have a pointer to go to these memory addresses. So instead of having to push these elements down, we just have to break the chain between 1 and 30, create the chain between 1 and 23, and create the chain between 23 and 30. If we want to delete it, all we have to do is restore the link between 1 and 30. Now, this is a simplified view of what actually happens. So what really happens with a linked list is you have to have two values. One is the actual value, and the next is what it's pointing to. So this could be in a very different memory location than this element or this element or this element. So what that does is it gives us some flexibility and some freedom that if we add another value here, say 23, all we have to do is just change this pointer from 1 and change the pointer from 23, the value, to 30. So that's a very fast way to do it. We don't have to push down any values. So if we delete, all we have to do is delete this value here and just restore the link from 1 to 30. So it's basically bypassing that memory allocation. In the next mini lecture, we'll talk about garbage collection, but for now we can just assume that we're not doing anything with this. We're just basically going around it by reassigning the pointer from 1 to go to 30. So this is the program we saw in the example, and we can see the performance hit that it takes. And again, they're using a smaller example. They're using 100,000 and 40,000. We used 150,000 and 50. But we could see the same kind of performance. I tried it with 1,000,000 rows, inserting 100,000, and it took a lot longer than this video takes to run. They have a video here showing it, and I suggest that you take a look at this video if you can. So what we're doing is we're avoiding this shifting problem. We don't have to shift values down because all we're doing is we're creating a pointer that is that linked list. And the link is the actual pointer to the next value. So in section 10.2, we start talking about linked lists. So what we have here is we have an initial node. And let's go to BlueJ and take a look. So here in BlueJ, we have a public class that we define, int node. We declare two private field members. One is dataval, and then the next is next node pointer. So this is going to have the pointer to the next node. So we have int node, which is a method, and this has data value 0. So this is what we're doing is we're declaring a constructor. This is a constructor. And then we also have another constructor and a third constructor. So we can either pass it with no values, no parameters. We can pass it with an initial value, and we can also pass it with initial value in the next location. So we have 3 different ways in which we can construct one of these nodes. Okay, so we have a couple other methods here. Notice they're declared public and void. So they're not going to return anything. So insert after is one of the easier conditions. So we're just going to take, and we have the int node, right, of type int node and node location. So what we do is that's going to be the temporary next, and you can see we reassign the pointer to point. Remember we had 1 and 30. What we're doing is we're inserting that 23 in there. So we have to reassign the pointers and we're using this temporary value to hold the pointers while we reassign it. You can follow the logic here. So if we ever need to know the location pointed by the next node, this int node get next is what we have. So it's going to return the node, right? So this is the type of return value. This one doesn't return anything, it just prints out the value. So taking a look at what we can use to call it, we have this custom linked list, okay? So in this class, we declare in our main head object, current object, and last object. And then we have a loop index. They like to declare them here. I would simply just declare it here and save myself a declaration because it's really just for use in this counter, but it's up to you. So this just appends 20 random numbers. And again, what we're doing is we're using the random object here to just get some random integers and then inserting them. Okay. So we're inserting 20. What we're doing is we're getting a random number that is in the range of 0 through almost 100,000. And then the current object, we call it with that random number. So that's what we're going to do in this insert. Remember the new. It creates space in the heap. And then what we have to do is we have to append what we do is we append the current object here using this. So last object dot insert after. So this is adding it on to whatever we had at the end of our linked list. And then we say that the last object equals the current object. We do this kind of to update where we are in that linked list. And then this involves printing out the linked list. So let's go ahead and run this and see what we get. First, we're going to clear out, oops. So we made changes here. So I'm going to compile it. Then we're going to run it and see what we get. Okay. So what it did is it printed out these 20 numbers. These were randomly created, and it just added them to the end of each. As it added one, it updated the pointer to the next one. So it doesn't put them in order, it just randomly creates 20 different elements. So I ran the more advanced version, which actually does more. So what we're doing, and I'd follow this, is when we're doing this, we have area and memory. And so what we're doing is we have a pointer to where this is allocated. So we have our data value, which is our head object, and the next node pointers to null. Because all it is, it's not pointing to anything. It has nothing left, just like this picture illustrates. Next, what we do is we indicate that we create a second object. And now what we need to do is we need to make sure that we can get to that second value. So what we've done is we've made it so this points to memory location 84. So this, remember, this is our head node. This is our second, this is pointing to the second node, which has the value 555, and that points to null. So just like the picture shows, we've got two elements, the first one pointing to the second one pointing to null. So now we can continue to add, say, other values, and notice that we're building this by using memory. And as we update it, it continues to add to this chain. And right now it looks like we're running out of space, but really, in reality, we've got more space than this. So we don't need a whole lot of variables to manage this whole list. This is the code that we ran, and this is similar to the result that we received. You can see that just this little bit of code can help manage an entire linked list. And that linked list is a structure that's stored within the heap, which allows it to grow. Now, I'll skip over this here, this exercise, and I suggest you look at this challenge activity. If you have any trouble with it, let me know. Then last, we're going to look at memory regions, the heap and stack. Okay, so we have a lot of different aspects. Code is stored in one area, and then we have static memory. What we mean by static memory, these are the variables that we declare with that keyword that says static. So these don't change through the life of the program. Then we have the stack. So here's a nice illustration of the differences. A stack and a heap are different types of data structures. A stack is a linear data structure, so it holds values as we push down and pop out, whereas the heap is more dynamic. It's hierarchical in structure, and it allows us to access things more randomly. The access speed for the stack is faster just because it's more organized and it's managed by the operating system. So we don't have issues of fragmentation. In 10.4 and 10.5, we'll talk about garbage collection. So garbage collection happens on the heap, and that's one of the concerns we have, whereas the stack, we don't have to worry about this issue. One of the key issues that define the heap versus the stack is what we store on them. So local variables are stored on the stack, whereas global variables and objects are stored on the heap. Because the limit of space is more carefully managed with the stack, we have to be careful. We can have stack overflows, for example, whereas the heap does not have such a specific limit on memory size. And one of the other differences is, remember, when we have a stack, it's pointing to an area of memory that's allocated. So that pointer allocates memory on the heap. But we can't resize the variables on the stack because they're placed in a linear order, and to resize a variable would be a lot of trouble. Whereas in the heap, we have a lot of flexibility. Just like we saw with these linked lists, we can resize our variables and make them much larger or smaller depending on what our needs are. So again, memory is allocated in a contiguous block in the stack, but we have random allocation of memory with the heap. So there's also a method area. This is where we have all the different data stored according to this example. Let's go through it. Let me make it a little bit larger. And so initially we have a bunch of code memory. That's loaded in first. And then we load our static variable, which is 33. Notice the static keyword. That indicates that that variable will not change its value for the life of the program. Next, what we do is we have a couple of variables. Notice that they're what we call our primitive data types, and here we're allocating them to the stack. Next, we use the new keyword. That is an indication that we will be using the heap. Anytime you see the new keyword, that tells you that the heap is involved somehow. So we, again, are creating my integer as a null, and notice that this is running the program. and then we deallocate the memory. So that's taken off the stack. We'll get more to that in garbage collection. So once we're done with the program, notice everything from the stack and the heap are disappear. The code is still loaded into the code memory area, and the static memory still holds the static variable. So that's it for chapter 10.3.